Okay. This is our lecture number 24, and this is related to uses of the radiations alpha, beta, and gamma. So there are so many uses for them. Like you can see here, the uses are they are used as a household fire alarms. They can be used to irradiation of food to kill the bacteria, and they can be used as sterilization, means cleaning of the equipment through gamma radiations, plus measuring the control thickness, measuring and controlling the thickness of a material. We can also use them as well. Plus, this is used as a diagnosis or a treatment for a cancer as well. Like in a household, the important thing is in the household thing, we used alpha radiations. Why alpha radiations? Because alpha radiation ionize the air with the detector and creating a current. So alpha emitter is blocked when the smoke entering the detector, right? So basically, the alarm is triggered by the microchip when the sensor no longer detects the alpha radiations, right? So there can be other things which it is used for. Now, it is also used for the sterilizing. When you say sterilizing, it means cleaning of the medical equipment, right? So, gammas is most suited to this because it is most penetrating out of all the types of radiations. It is penetrating through to irradiate all sides of the instruments. Instruments can be sterilized without removing the packages. Okay. So the source of gamma radiation used to sterilize has a half-life around. Now half-life is something which we're going to study. Half-life is a time in which the radiation, the product is become half of its quantity. Now, irradiation food to kill bacteria using gamma rays. So food can be irradiated to kill any microorganism. So basically, that gamma radiation is also used to kill the bacteria that is present in it. Plus, it is also used to measure the thickness of a material using different radiations. Alpha particles are used for the thinner material because they have a low penetrating power. Alpha particles are used for a thinner material. Okay, gamma radiations can be used for a thick material because they have a higher penetration power. So these are used to actually uh, finding the thickness of the different type of materials there. Now, another very interesting thing, they are used in radiotherapy as well, like for the treatment of cancer, and even like radiation can kill living cells. So some cells, such as the bacteria and cancer cells, are most like dangerous. Also, these radiations will be able to kill them, and so basically, cancerous cells can be killed by that gamma radiation. Plus, the diagnosis can be possible through the gamma radiations as well. Okay. Next is danger. What are the dangers? Very simple thing is the biggest danger for ionizing nuclear radiation can be damaging living cells, living things. So they can damage in how many ways? Cell death, mutation, means they can be corrupted or whatever, and forming a cancer. So if atoms that make up a DNA strand are ionized, the DNA strand can be damaged. And if DNA is damaged, then the cell may die, and DNA may be muted when it is replicated. So, if a mutation cell replicates itself, then tumor may develop. This is example of cancer, which is significant danger for the radiation exposure. Acute radiation exposure can have other serious symptoms. So remember that if you put it up like that, like for example, if the exposure is bigger, the danger can be bigger. The exposure can be less. Then there is still a danger like skin burn can be one of the danger for that. Or you can say radiation can reduce the amount of white cells in the body and making a person more sophisticated is, you can say sophistical, or you can say more sus it can be more infected by lowering their immune system. Okay, so that happens like that. Now, what are the safety measures which you need to take? Safety measures, just as simple as that. Make that box or place that box in a lead lined box, so and keep it away from the people distance which is actually radiating radiation source, right? Because definitely lead is quite safe, it is absorbing the radiation. So if you place it into lead box, then it can be safe. Plus, less and less exposure, and minimize the amount of time you handle the source. This is very important. Minimize the time. During use, keep yourself away from it. And when handling the source, use different type of tongs and special cloths so that you can save yourself from the exposure of these radiations. Next is radioactive materials such as used nuclear fuels are transported in a special container called casks. Casks can withstand extreme conditions such as fire, cold, and being submerged in water. Dispose it in a better place, always dispose it. So, if an isotope has a long life, then the sample of it will decay slowly as the time will be very small, like it becomes half of its quantity. But we will talk about this as I told you. What is a half life? So, source with a long life values presents a risk of contamination for a much longer time. Radio waste with a long half life is buried under to prevent it from being released into environment. Okay, so correct disposal is very important. Now, safety precautions in general. Reduce time. Exposure time should be as less as possible, and definitely shielding is very important. Shield yourself from them by wearing cloths and all that. Use tongs while using it. Distance yourself from those areas. Okay, and shielding reduce the danger of what? What is shielding? Radiation shielding is a barrier place between the radiation source and a person or area to protect them. The purpose of shielding is to limit exposure to radiation at a certain location or a time. So bearer absorb the energy from the radiation source. So technically speaking, you need a lead apron to reduce the exposure from that, because lead will absorb it and it will simply save you from the exposure for that. Now, how to detect it? There are different equipments which are used for that. One equipment is named as a cloud chamber. By the way, alpha particles are detecting using a cloud chamber or a spark counter. There are different type of cloud chambers. A cloud chamber contain a metal plate on a bottom and cooled using a dry ice. So a transparent view film at the top with the light source on that is observed to identify what happened. The major part is very simple because this is not a part of our syllabus, but for the time being, I can simply tell you that alpha particles can be detected by cloud chamber. So electric field at right angle to the chamber is formed, which we say that it is basically an alpha particle. Okay. Then we have a spark counter. The equipment is like that. And what is that spark counter? Spark counter is actually detecting of a beta particle and a gamma particle. Now remember that when you say a count rate is a number of decay per second recorded by the detector or recorded by the counter. So count per second or count per minute is a unit. The count rate decreases the further the detector is from the source. It's very simple. The detector is further away from the source, the count rate will be as reduced as possible. Now, what is count rate when you say that? Count rate means number of counts reduces as the time progresses because it's continuously decaying, right? So how to detect the beta radiation? So basically, if you just say that, if you just see spark counter, the spark counter is using, I mean, beta and alpha particle, technically speaking, mostly. But the third one is important, which is actually in our course, we called it detection of beta particle or gamma particle. This can be used by, I mean, the equipment used for that is called as Geiger-Müller tube. So most common device used to measure the detection of beta particle and gamma particle is this one. Each time it absorb radiation, it transmit an electric pulse. Now this is very interesting. Check this out. This is a device that actually gives a pulse, right? Pulse means electric signal. And when it provides or gives the pulse, right, to the counter machine called a counter. And this makes a click, shows or display the count rate on the screen. The greater the frequency of a click here, the higher the count rate seen, and the more radiation the Geiger-Müller counter is absorbing. Right. So this is Geiger-Müller counter. If you check this out, the example is being done for you. The number of decays is 16,000. The time is 1 hour. So in 1 hour, 16,000 decays. So if you just divide it, you will find out that 4.5 decays per second. You just divide it by 3,600. So it will provide you number of decays per second, right? So it is decays per second, 4.5 decays per second. Now, afterwards, we have another small topic. What is meant by background radiation? Now, background radiation is a low level radiation which are always there. Okay. So, background radiation is always there, whether there is a nuclear radiations or not, but background radiation is always there. That is the reason when you do when you use this Geiger-Müller uh, tube to measure the count per rate, it will always provide you some count rate. Okay, even in the absence of nuclear radiator source, it still provides you some count. Like for example, in a room when there is no nuclear source or whatever, so it provides you, let's suppose, 4 counts per second. The question is where this 4 counts per second comes from. It is the background radiation, which is always there. So you need to see that background radiation as well. Very simple to find out, and very simple to see that if there is a no what you say nuclear radiation thing, and still you find that count rate or counts per second, it means it's a background radiation. So always whenever you find out the count rate, the corrected count rate will be you need to subtract the that count rate, which is basically the count rate of background radiation, from the count rate you just measure. So corrected count rate will be count rate minus the count rate of the background radiations. All right. So what are the sources for that? We got a sources, cosmic rays from the space. So basically, high speed proton emitted from the sun produces a small amount of gamma radiation as they enters the earth and atmosphere. So this can be a source. Then we have carbon 1440. All organic matter contains small amount of radioactive isotopes. So it does have it as well. Then rocks and soil, small amount of radioactive isotopes such as uranium are found within the rocks and the soil. So uranium naturally decay into radons, which is emitted as a alpha source. So this can be that as well. Then we have food and drink. Remember that the background radiation also in the food and drink as well. Like banana contain relatively high amount of potassium and a potassium 4040, but low enough that does not cause any problem. It does have everything to do with a man-made source as well, like medical radiations, medical radiation from medical scanning and traces, nuclear waste, very small amount of radiation is emitted from the radioactive waste, plus nuclear weapons after the nuclear weapon is used, leftover nuclear residue is left in the area, and that fallout is an emitter of a background radiation. Right? So this is what the old background radiation is. Now there is a small topic which we continuously talked about is half-life, right? Now, what exactly is the half-life? That's what the question is. When you say half-life, the concept is very interesting. What exactly is happening? Because radioactivity means it's a decay, right? Like for example, you have 40 atoms, and the time it takes to remove or decay 40, 50% of the atoms will be decayed. Like if there are 40 atoms, only 20 atoms left. Or if you talk about kgs, out of which half of the quantity is removed and half of the quantity left. So what is basically the formula or definition for that? Time taken for the half of the nuclei of the isotopes in the same sample to decay is called as uh, radioactivity. I mean, half-life. The unit is BQ oral. There is another definition as well, which is also very, very important. It's for the activity as well, because activity generally means that something is decaying. Let's suppose initially, if the activity is 4 counts per rate, and when it reduces to 2 counts per rate, that time duration is called as half-life of the material. So even the activity reduces to half, or you can say the quantity reduces to half. So time it takes for an activity of a cycle decreases from 100 to 50% of it is called as also you can say half-life. So half-life is very interesting phenomena, and because of this half-life, there are so many things which are actually, so quantity become half of it, activities become half of it, sample become half of it, or half of the sample is decayed, is called as half-life. Now you check yourself. This is activity versus a time graph. Initially, the activity is A naught, it reduces to A naught by 2. That time duration in which this activity reduces to A naught by 2 is the half-life, right? Now check this out, that A naught 2 is reduced to A by 4. That is the second half-life. So it goes on and on and on, and it quantity will be reduced and reduced and reduced. So that will be your first half-life, second half-life, third half-life, and it is approaching to 0. But definitely it takes time to become 0. But initially it just decayed and decayed and decayed and decayed. Okay. Now we already talked about this safety precautions and everything. Now, questions related to this. Now, this is very, very interesting. Again, the half-life. Half-life can be measured of a decay. The half-life of a radioactive isotope can help us measuring the radioactive decay of a substance. The time it takes for number of nuclei of isotopes in a sample to half of the quantity. See, activity as well, half of the quantity. The graph, we already talked about this. Now, here the questions we have. This is very interesting. Now, there are multiple questions we have it related to half-life. First of all, now there is a formula which we need to memorize or remember, whatever you want to do. Formula is very simple. Amount left is equal to total amount divided by 2 into half-life, or number of half-life. An isotope of cesium has a half-life of 30 years. So half-life is given. If 1 gram of cesium disintegrates, so total amount is given. Over a period of 90 years. So 90 years. How will you find the number of half-lives? Very simple. Number of half-lives, 90 over 30. It means there are 3 half-lives. So n value is given. Now they are saying how many left or remain after 90 years. Very simple. Total is 1 divided by 2 to the power 3, and that will be equal to 1 upon 8, and 1 upon 8 is equal to 0.125 grams. So you just need to find the values and you will get the answer. In that case, selenium 83 has a half-life of this. This is again half-life given, which is 25 minutes. How many minutes would it for 10 grams, not time required, total time. So total time is required. And what is the total amount? 10 milligrams. And left is 1.25 milligrams. Simply place the values. Now, important part. How many minutes would it take for half-life is 25. So what to do in this? A selenium 83 has a half-life of that. How many minutes would it take for 10 grams of to decay and only have 1.5 remain? Now, very simple thing is just place the values here. So it will be 2n equals to, amount is 25, not 25. Amount is 10, and amount left is 1.25. So basically 10 divided by 1.25, it gives us 8, right? So it will be 2 to the power n is equal to 8. So it will be 2 to the power n is equal to 2 to the power 3. So n is equal to 3. So number of half-lives it takes is 3. And each half-life is 25 minutes. So 25 multiplied by 3 is 75 minutes. So answer is 75 minutes, which is 8 in that case. Check it out. There are further questions. We have it. Let me do one more for you, and then there are questions which you will be able to solve it. Even the answers are given. You can go through them. Formula will be same, no difference at all. Like in this question, what is a half-life? Now they are asking you the half-life. If 500 grams sample decay to this, now total amount 500 grams. Left is how much? 62.5 grams. Total time 24.3 hours. The formula is 2 to the power n is equal to 500 divided by 62.5. So 500 divided by 62.5. It's coming 8, which means that 2 to the power n is equal to 8, so n is equal to 3. It means there will be 3 half-lives, right? And now, what is half-life? Number of half-life is equal to total years divided by half-life. Number of half-lives, right? So 3, you simply divide it by the total number of years, which is 24.3 divided by 3. So 3, 8, the 24, 3, 1, the 3. It's 8.1 hours, right? So there are so many questions we have it on half-life. So half-life is a time duration in which a radioactive isotope becomes half of its quantity, or its activities, which is decay per second, reduced to half of its quantity, or you can say half of the quantity is being decayed, or half of the quantity is being left. Okay. So this is the end of this session. In this session, we have gone through some concept about the safety precautions, dangers and uses of the radiations. Then we went through background radiations, corrected, I mean, count rate and count rate, definitely. We have seen that background radiation is always there. You just need to subtract it from the actual count rate to find the corrected count rate. And then we have seen a small concept related to half-life. In the next session, that will be our lecture number 25th. In that lesson, we will be doing fission and fusion and radioactive, and definitely fission reactor. I mean, the reactor in which we perform fission reaction. And that will be the end of that session. So hope to see you in the next session. That will be 25th. This is the end of 24. Thank you for watching my video. Bye.